Okay, good afternoon, everyone. Today I will be talking about the parcelization vulnerabilities, their fuzzing and exploiting strategies in Android to achieve privilege escalation. And firstly, I want to do a brief introduction. My name is Qidan He, and also known as Flanker, and I'm a senior security researcher at Tencent King Lab, formerly known as King Team. And my main focus is vulnerability auditing, and fuzzing, and including iOS, OS X, and Android and Linux security. You can see there are no Windows. I'm not familiar with Windows. And I'm also a Pontoon 2016 OS X category winner. And about my team, and we are previously known as King Team. And due to some business requirements, our researchers now moved to Tencent King Lab. And our union team with the Tencent PC Manager has just won the Master of Pong at Pontoon 2016 about 2 weeks ago. Okay, now let's go to the technology part. And this is the agenda for today's talk. And I will first do an introduction on the binder architecture and its overview of these attack surfaces. And also, I will introduce how we do some fuzzing and our fuzzing strategies, our fuzzing implementation, and the fuzzing architecture. And thirdly, I will do a briefing on a case study, the CVE 2050-6620, and how we can achieve both info leak and code execution in a single vulnerability. And finally, it's a summary. So, what is binder? Binder is a core mechanism for inter-process communication in Android. And about 4 or 5 years ago, it is called Open Binder, and it's acquired by Google. And it is built for the core inter-process communication in Android. And the Android is a bit different. The Android kernel is a bit different from the Linux kernel. There's no system V IPCs in Android. There's no message queues, but Android still has shared memories. And so Android removes the system V IPCs to prevent resource leakage and to prevent denial of service vulnerabilities that we can create many message queues and many SAM phones to cause the device unusable. And it is not in the POSIX implementation until 2015 where the binder architecture is finally merged into the Linux mainstream kernel. And the binder has many advantages for it is also why it's chosen for the core architecture for Android, because it has many advantages. And the first of which is building a reference count object, and it is done at the C++ level by all objects extending ref base. And it also implements a death notification mechanism, so that, for example, one application registers a callback for a GPS location moves, and the binder architecture will be used to notify the end applications about the movements of the user's GPS location. And the binder also provides the ability to share file descriptors and shared memory across process boundaries, so that we can achieve efficient file sharing and memory sharing. For example, the Android share memory is actually passed via write file descriptor. It is encapsulated as a file descriptor, and also the mediaserver plays median file actually via a passed file descriptor. And the binder also supports synchronized and asynchronized calls. The most obvious example for asynchronized calls are activity starting, service binding, listener registering. We can see it frequently in everyday Java world. And for synchronized calls, you can just directly call a binder service, and after it returns, you can get a result. So the iBinder class is the key of the binder heart. And the procedure of calling remote service is as follows. The remote service is mapped to a handle, and first you should get a remote service, and the remote service is mapped to an integer handle. And the handle will be constructed as a BP binder. And the BP binder will then be passed to the BP interface via the S interface call. And for example, for the crypto service, the class name, the inheritance is actually looks like a new BP crypto and extends from BP interface with a template name iCrypto. And the iCrypto is the abstract business logic interface. And there are many virtual functions in the iCrypto, and end developers should implement this. And the BP interface extends from iCrypto and the BP ref base to provide the basic ref count. So when an end application made a transaction, the binder token is written together with the transaction command and the transaction data using IO control to DV binder. And the binder driver will query in this internal mapping about from binder token to actually remote binder service, and it will relay command to appropriate service. And the BB binder is the service part implementation of the remote service, and it is usually some subclass of the BN interface, and it will handle incoming data in the onTransact function. And we can usually find many memory corruption bugs, information leakage bugs here. And we will use some diagram to illustrate it. So this is a bit complex looking inheritance diagram, and we can see on the top of the tree is a ref-based class. The ref-based class is a ref counting based class in Google's C++ language, and it is the father class of all the class listed in the diagram. And the I interface is actually an abstract class implementing a function called onAsBinder. And we can see that the BN interface, which is the implementation at the server side, it will subclass from I interface and the B binder. And on the other hand, in the client Parcel class, it is called the BP interface. The BP interface will implement the I interface and the BP ref base. And there is a line connecting BP ref base and BP binder. It is because the BP ref base will hold a reference to the BP binder, and the BP binder will hold the handle that will maps to the remote service. And there are also some other classes here, like the process state, like the IPC thread state. And this is actually the worker functions. The worker functions that will pass through and that will receive and pass through binder data. And we can see on the left upper corner there is a function called transact, and you can see the first function is the IIT with driver. The second function is write transaction data, and the third function is wait for response. This is like the internal function that will actually release the binder, the Parcel data. And we can see here that there is also a class called iCrypto. The iCrypto class extends from iInterface, and it will hold the actual business logic in the class. Like, for example, Android crypto service provides some functions like a query for crypto scheme, like a query for crypto plugin, and the iCrypto will contain the per virtual function names for this functionality, and the BN interface, and thus the BN crypto will actually implement this function at the server side. So we can reach a conclusion here that BP or whatever service, like a BP crypto service, like a BP HDCP service, that all kinds of these services in Android, they hold a client calling convention that they will describe which kind of parameters, how many parameters will be passed by parcel.write through parcel.write string, write long, or write also some primitive types. And the BN service like BN crypto service or BN HTTP service or other BN XXS service will hold the transaction logic in the server side. Also, we will have a question here that besides passing primitive data types like integer, like string, or like long, like float, how do they pass complex data types? And here we will introduce a concept called data boxing and unboxing. And we can see that the Parcel class defines basic data types like modules, like int, like string, like strong binder. But for complex data types, we need to build them on modules. That we need to split them into the basic transaction types. And there is no type of information in the transaction stream. And the receiver side will just interpret the passing data types, passing data stream, and think it won't perform a type check. So we can see some profit here after. And the data boxing and unboxing in Java, in the Java world, in Android, is a bit different. The Parcel.java also defines basic data types, but it has one more, the serializables. The serializables has 12 info string in their data stream. And so there are also some historical vulnerabilities here that if this class is actually serializable, if it actually extends from serializable, and this is CVE 2014-7911. And also in last year, there's also a vulnerability relating to data boxing and unboxing in Android Java world. That is, all the fields in this class instance secure to accept serialized serialized input from outside world. And this is CVE 2015-3825. And I will not elaborate here. And if you are interested, you can consult their related materials. So after introducing the binder architecture, we now have some ideas to do some fuzzing. That fortunately, the Google developers, the programmers at Mountain View, they follow the good coding patterns. So we can do an automatic static code parsing to determine that for each binder interface, for each binder service interface, which kind of parameters they will accept. We will search and collect all BP class and BN class definitions, and we will pass out the interface arguments. We can see that in the screenshot, we can see that there is some functions named data.writeInt32 or a write interface token. Write interface token is actually a string. And also in the lower part, we can see a data write key 16. That means that it writes a byte stream with length 16 to the Parcel. So with this knowledge in hand, we can know that what parameters this binder service will accept and how they will appear. So we do a pre-parsing on this argument information, and we will store it in like a database or JSON or whatever you like. And we will do an agent server design to do the fuzzing, because we will run the agent on an Android phone, and the agent will accept this input from server via socket or direct command line arguments. And the parameter, we have the parameter info, but how to fill the parameter? For example, in this picture, we see that the argument needs an int. First, it needs a string, then it needs an int, and then it needs an int again, and it needs a byte array of 16 length and byte array of 16 length. So we need some logic to feel that which integer we will use and which content of byte array we will use. So in this part, I use some pre-filled contents, like some integers that will frequently triggers integer flow, like FF, or like this. And we also record some. We'll record some binder transactions in the normal applications, and we'll do a bit flip, and also we'll do a pure randomized fuzzing. And take mediaserver as an example that if we trigger the crash in mediaserver, the mediaserver will reboot itself, and we'll see that its PID has changed. So we can retrieve the crash log in in logcat and tombstones. So also, I have introduced the fuzzing strategies in the native land, but for the Java land, the story is a bit different because in the most objects in Java land, the transaction is passed in the form of serialized stream, like a serializable or like this. For example, the java.language.string and the java.language.float or like this. They are passed in a format of serialized stream. So for this part of fuzzing, I use some intercept and mutate strategy. So I do I hook into a normal application and I mutate the byte stream for each class and mutate the type info string header in the Java data stream. And this fuzzing strategy triggers a lot of crashes, but unfortunately, because the safety nature of Java language, we do not get exploitable memory corruption bugs. We only get some OM or infinity loop like denial of service bugs. But for the native land, we have triggered some efficient crashes, and we will analyze one of the bugs later. So also, a natural idea comes with us that we can integrate the fuzzing with ASAN. The ASAN, and I think as we all know, the ASAN is the address centralizer, and is very efficient in catching memory corruption bugs. And the AOSP provides way to enable ASAN on libraries and also the whole platform. We successfully compiled the ASAN on the whole AOSP on Nexus 6, but we didn't success on other physical machine models. And we also have successfully build ASAN in ARM, but we didn't success in building on x86 machines. And I have written a ticket for about the x86 support to Google, but there is no response currently. So using the following command lines, we can enable ASAN support on the whole Android device, but I have only success on Nexus 6 and not on other devices. And also, we also have an idea of integration with AFL, and because why we have the idea? Because the binder transaction actually some byte stream data passing around, and it would be great that we can use some incremental fuzzing strategies, fuzzing tools like AFL. That, for example, we can first collect some normal data and use AFL to mutate and monitor it. But unfortunately, we encountered a big difficulty in compiling Android core libraries on AFL, so it is still a work to be done. Okay, now I have introduced some basic architecture and fuzzing strategies and in the binder services, and now we'll come to the case study part. So this is Android 24123.723. It's one of the bugs we reported to Google in last November. And it is a classical bug of the data of vulnerabilities in data type parsing. We can see there is a type called a message. The a message is a complex data type that implements its own marshalling or parcelization function. And we can see that a parcel is provided to the a message, and then it will pass the parcel and retrieve the content from it and construct it itself. However, there is a auto-bound access and auto-bound write here, because we can see that the m number items is determined by the incoming in 32 data. We can see in the 1, 2, 3, 4 in the first line that it reads the number of items from the Parcel input, and then it will loop through this counter and do some writing or reading. Unfortunately, this integer can be totally determined by us. We can set it to a very big integer, and thus we can easily cause an auto-bound access or auto-bound read. The bug itself is not complex, but to trigger it, there is some interesting stuff to be notified. That in order to trigger this vulnerable code path, we need to pass a callback. We need to pass a callback to the privilege process. And first, we need to construct a BN stream source and pass it to the median server. The median server set data source function. And when certain type media file is played, as we can trigger it, the BN stream source set listener will be called. And the client, that is our attacking process, will get a reference to iStream source. And with this callback in hand, we can pass the malicious Parcel data back to the iStream source issue command, and the server side of this function will interpret the malicious Parcel data and finally triggers the OB bug. And also, in last November, we also reported an information disclosure bug in system server, and it's actually an integer overflow in the motion events on Parcel. We can see that as the same as a message that this motion event, it will receive the Parcel it will blindly trust the incoming Parcel data, and we can see in the lower line that there is a vector, and the vector capacity is determined by the integer multiplication. And so we can easily see that here there is an integer overflow here, and if we provide two big integers, and the vector size will be very small, and in the following access there will be memory corruption bug here. So after the two bugs, we will finally demonstrate an exploitable ones, that the auto-bound dereference in the iMedian codec list, and how we turn this bug to achieve both info leak and code execution. And first, what is a median codec list? The median codec list is an class in Android that provides how many median codecs this phone will support, and so that you can use it to play media. And if your phone doesn't support a specific codec, then you cannot play a specific media. And so the Android system provides a service called a median codec list to tell the end user that which kind of codec it supports. So there is a function name called getCodecInfo, and we can see that this is the server-side implementation, and we can see that an index is passed in the data read in 32, and the index is passed through getCodecInfo. And if the info is successfully retrieved, it will write back to the Parcel in the info write to Parcel function. If it has failed, then an invalid value will be written in the Parcel, and the user will be notified of it. So let's go back to check the getCodecInfo function. Unfortunately, there's no bound check here, and we can see that index is directly passed to a vector's item add function. And to trigger this, we craft a quick POC to trigger this, and we get a crash here with this. And on the first glance, we can see that the fault address is at 0x84. In the right hand, we can see there's a fault address, and the rling is a value that is very small, and we may think that it is a null pointer dereference. But deeper analysis proved us wrong, that it is an actually exploitable one. So first, we need some domain knowledge of this vector in Android, that the mCodecInfo is actually a vector of the strong pointer of the median codecInfo. And the vector is a linear vector storage, and it has a size in the header and a capacity in the header, and it has a pointer to a linear vector storage. So we can see that what is stored in the linear byte storage is a pointer of the median codec info. And the GDB will clearly reveal that. We can see that on the first part, at the 5C offset, it is actually the storage pointer of the M codec infos. And at this part, we can see there are many median codec info pointers. And at Nessus 5, there are 33 codecs, which makes it false at the gmalloc 160 region. And this is very useful for our following exploitation. So we now proceed to the operator's index function, and we can see that there is a check. There seems to exist a check here that an index should be smaller than size, or it will do a log fatal if. But unfortunately, it is stripped in release build. That is, this macro is not effective on release builds. So we can see that the index is directly passed to the addressing function, and we now get an OOB. But it is whether an OOB read or OOB write or whatever, and we will see later. So also we need some knowledge of the strong pointer. The strong pointer is used in the ref count mechanism in Android, and the ref counter, the strong pointer is. It is not a virtual class. It only has one field, that is its holding pointer. But there is an interesting function here called INC strong. The INC strong is used when a strong pointer is constructed, a strong pointer is passed from one to the other. So we can see that as we see, the get codec info returns the SP median codec info, and so it is encapsulated in the strong pointer. So when it is passed from one function to another, the implicit INC strong is called. So an auto-bound median codec pointer. So we can see there is a possibility of PC control here. And we can see in line 338, there is a code called refs, mbase, and the onFirst ref. And the onFirst ref is a virtual function. And so it shows us a possibility of the PC control. So the following assembly will clearly reveal that we can see first media codec M codec infos will be retrieved, and finally is passed to an INC strong. We can see that you cannot see the INC strong in the source code, but in assembly it will clearly reveal that there is an INC strong. The INC strong is called. And finally, after some address dereferencing, we can finally reach a BXR1 here. So the offset is quite complex. First, the R-link retrieved from an offset we can control in the item add function, and then it is passed to INC strong. And we need to bypass this check that M strong should be equal to INT strong value to finally trigger the BXR1 control PC at the last location. So we still need some heap fengshui here, and the interface we chosen is the IDRM provide key response. And the response, it is a very useful function because the passed-in data can be passed in base 64 format, and it allows for non-ASCII data and both zero terminators. And it is stored in the map structure of IDRM, that is, there is no free, no GC, and it will reside in the heap of the median server. So also there are also some primitives that can free this, but I will not elaborate here. And also, thanks to the gmalloc that he introduced in the new version of Android, the region, the 160 region is allocated adjacent, so we can actually. And also, the median codec PTRs is allocated allocated next to a free region because the 160 region is not a frequently used region in Android. So we can do a heap 3 here and to point the auto-bound index to a region we can control. So we can see that in this screenshot we have successfully redirected the program counter to 61616161. And also, so we have now resolved the problem of PC control. There is also another big problem that we can see that for Arlene, it is pointing to B3003030. That is, this is a heap address that we use spray to push the heap and push it to address of the B3003030, and we will put some malicious content we controlled there. And for Nexus 5, this is a very stable address, and for other phone models, we may need a bit change. Also, so we have finally resolved the problem of PC control here, and we still need the info leak due to the modern ASLR mitigations. So let's turn back to the write to Parcel function. We can see that the median codec info, as we recall that after the median codec info is successfully retrieved, it is passed back to the Parcel. So if we can craft a valid median codec here, we may be able to retrieve back some information. And the answer is yes. So we look at the write to Parcel function. The first, the M name is A string. It's an A string in the foundation class of the median server. And after the A string, the return an int, and a vector named M crux. And all the items of the M crux will be returned, and then an M cap size, and then all the content of M caps will be written. So the A string is a string representation in median server, and we can see that it contains two fields. One is the size field, and one is the char pointer. So if we can control the char pointer and the size, we can achieve an arbitrary memory content rate. And for the memory layout of the median codec info, we can see that first it's V-table for 32-byte device. As a head is a V-table, and at 4 offset it is a M-refs, and 8 offset it is the M data of the A string, and at next offset is the M size of the A string. And also there are some critical fields we need to take care of to avoid crashing median server. So we want to achieve an arbitrary read here, and we can make the M name points to an address we want to read, and to make the M cross size to 0 and the M cap size to 0 to avoid crashes. And so we can finally achieve an arbitrary readability here, and we have some conditions to avoid crash as offset 32 and offset 52. And also we need the M refs plus 4. It will dereference to a valid location to avoid crashes as the Android atomic INC. And also we need the C, it should not be equal to the INT strong value. And if we can meet these conditions, we can achieve a successful info leak. So our info leak solution is as follows. We spray content or size for a page size to push heap to reach a fixed point address as the B3003010. And the first 16 bytes is metadata of the GE_malloc. So we will secondly do a spray on the content of size 160 to filled with the address, the heap address, and it will fall right behind the vector's array storage. And then we trigger an autobound to relocate the median coding info to this heap to the spread heap address, and we can retrieve a leaked memory content. And for our solution, we retrieved out the text section of the median server, and we will do a comparison of the text section on our pre-stored domain knowledge text section to determine the offsets of the dynamic library. So here are some functions to set up the raw buffer. And we can see here we have successfully leaked out the text section, and compared with GDB, we can prove that we are right on this. So for RP and the shellcode section, I will not elaborate here because there are some previous research from Gongguang. Because of ASAN Linux, you cannot directly run bin.sh. You need to inject the BZBox, and it is a very time-consuming task. I will not elaborate here. And finally, I will release the POC afterwards, maybe after some days. So this is all, and this is some credits. And okay, do you have some questions? Okay, thank you.